Okay, so I'm not going to talk about Nash. Well, I am. You see, I changed the title and added Nash. Originally, there was no Nash there. In fact, there's going to be a lot of Nash. So most of what I'm going to say, in fact, I realize now that but most of it is joint work with Dean Foster. Oops. Okay. And there are papers that you can find on my web page, which I keep it updated very much because I'm the heaviest user of that web page. That's the way I find my papers. Okay. So that's the most relevant paper on which I'm going to talk. And oops, I have to do it this way. Okay, so not Nash equilibrium, calibration, forecasting. Okay, let's talk about forecasting. Okay, what's going to be the weather tomorrow? Okay, let me open my app. You know, I can tell you something. It says there is going to be, or maybe not tomorrow, but 2 days from now, or on Saturday, I think, there is a 34% chance of rain. That's what, this morning, that's what it said. 34% chance of rain on Saturday in Oxford. Okay? What does it mean? Well, 34% chance of rain. So usually the story, when people say probabilities, what do they mean? What do they mean by the probability of tossing of a coin coming up heads is a half? It doesn't mean that I get heads, tails, heads, tails. It means in the long run, the frequency of getting heads is 1/2 of the number of tosses. So that should be the same way we interpret our 34% chance of rain. In the long run, there should be about 34% days of rain among all days. No, among all the days when I said that the chance of rain is 34%. That is called calibration. So calibration just says, okay, maybe I'll stand here. Then automatically when I point that way. Yeah, okay. So when the forecaster says the probability of rain tomorrow is P, the interpretation of that is, you think it works? No, you have to be very, so that's electronics that you have to be, you know, really, okay, very close. Distance shouldn't matter here. Okay, so forecaster is calibrated if for every forecast P that is saying, 34%, 70%, whatever, in the days when the forecast was P, the proportion of rainy days is P, or close to it. Okay? That's calibration. Okay. Now, okay, here's a theorem. So, look, I have nothing in my sleeves. You see, I came with short sleeves. It's on. I can guarantee calibration. Not in Oxford, not in Israel, not at the North Pole, any place you put me. Okay? Not only that, even let's let Bary, our great organizer, to be responsible for the rain. We let Bary, who is a very smart person, every day decide on the rain. I give a forecast. Bary decides whether there will be rain or not. His only aim is to make me look bad. Okay? You're allowed. It's okay. Okay? He won't succeed. Won't succeed. Okay? And that's a beautiful theorem. I'm emphasizing, sorry. So that's a beautiful theorem. Foster and Vora proved it. 94. Was published in 98. It's not that Dean and Ricky were lazy in submitting their paper. They kept submitting the paper again and again. They would get desk rejection one after the other. Without knowing anything about the weather you are able to predict, no way, something is wrong. Not that they found a mistake in the paper, but this can't be true, okay? So it took them a few years to publish it. I have a very short proof. When I heard Dean give a talk on that in Jerusalem, I came up with a very short proof, which in fact comes with a challenge that let me repeat it here. So the proof goes like this. It uses the minimax theorem. And it says the following. Suppose I know the strategy of the rainmaker, of Bary. If I know the strategy of Bary, I know every day, it's a mixed strategy. Bary may mix. I know every day what's the probability that it's going to rain. What's going to be my forecast? Well, that probability. I'm going to be calibrated. End of proof. Well, there is a law of large numbers there and a few details of making it discrete, But it's a trivial proof using the minimax, giving you an amazing theorem. Because if I know what the weather is going to be, of course I can give calibrated forecast. From this I deduce that I can give calibrated forecast knowing nothing. No way. So challenge, find me a more striking use of the minimax theorem. Okay, for 20 years I'm saying that, and I have yet to find something better than that. I think this is really striking, which shows you that the minimax theorem is not just a triviality that some people may think. Okay, there are lots of other proofs. There is a proof using Blackwell approachability of Andreu and myself. There is a twist on that by Dean Foster that makes it even simpler. And in fact, there is a much simpler one that uses, by Dean Foster and myself, that uses something that we call forecast-hedging. Okay? We like the name forecast-hedging, has the right initials, as you realize. So let me explain to you what forecast-hedging is. So here is a nice graph. On the horizontal axis, I have the forecast, which is between 0 and 1, the probability of rain. On the vertical axis, I have the frequency of rain. So perfect calibration means that the frequency of rain exactly equals to the forecast. So it means everything is on the diagonal. Everybody follows? Very good. Okay? So suppose now that I am, after some history, and this is the graph that describes what has happened until now. I've only used 0, 20%, 40%. I only used 6 forecasts. And for the 0%, I had something, I don't know, 80% rain. For the 20%, 60% rain, whatever. That's a history, okay? It's completely arbitrary. Somebody else is talking together? A nice echo. Maybe this shouldn't work.
I think they're running some tests over there, actually.
Oh, I see. Okay, that's a hidden variable. Okay. Okay, so that's perfect calibration. Okay. Now, what's forecast hedging? Forecast hedging does the following very, very complicated thing. Okay. Yes, pressing just button once. That's very complicated. Okay. So you find one point above the diagonal and one point below the diagonal. How do I know that there is such a thing? Sorry, in a moment. Join them by a straight line, okay? Take the intersection with the diagonal and forecast those two with probabilities that give you on average this point. That's it. That is going to be calibrated. Okay? How do I know there is a point above and there is a point below? Well, 0, the point for 0 must be above. Because when I said 0, I must get greater equal 0, above in the weak sense. I must get at least 0% rain. And when I said 100, I must get less than 100% rain. So if the first dot is above and the last dot is below, at some point I must go from above to below. That's life. Okay, so that is, that is the forecast hedging procedure, which is a simple, you can't do much simpler than that, okay? I don't need anything, any computer or anything. I just need this data, which I keep updating every day, and I just find a point, and if I have more than one intersection, choose the first one or any one you want. That's it, as simple as that. The fact that it works takes a little work to prove it. It's not as trivial as it sounds, but this works. This is calibrated, okay? And that's forecast hedging. And just to show you, in a moment I'll explain why we call it forecast hedging. I'll show you some graphs that I took from the web. That's from 538. That's Nate Silver. Okay? It shows you calibration plots. They call it calibration plots. You can see they are pretty close to the diagonal. Well, for sports, for sure. For everything, for politics, a little less. Okay? Another one was election betting odds, whatever. Okay? I think I missed the slide. But anyway, so let me tell you this. I don't know, maybe it will appear later. Why do I call it forecast hedging? We are talking about forecasting. Forecasting says something about the future, There is no forecasting here. I'm not saying anything about the future. I have no clue what Bary is going to do tomorrow. He's a smart guy. I can't outguess him. There is no forecasting here. There is something that we call backcasting. What I'm really doing is the following. I'm looking at my track record, what has happened until now. I'm making a forecast that has the following property. No matter what the weather will be tomorrow, my track record can only improve within epsilon. It's exactly like hedging in finance. Hedging in finance means I have a certain option, you do it through options or some other financial mechanisms, that no matter if the stock goes up or down, my position stays the same. No matter if the pound relative to the dollar goes up or down, I'm an exporter, and I want to make sure I'm hedging the risk, I play a strategy such that regardless of what's going to happen, over which I have no control, my position is going to stay the same. Insurance is another kind of hedging. Yes, I pay the insurance, then I don't care if my house burns down or not. Well, I do, but never mind. Financially, I don't care. My position stays the same. That's hedging. Forecast hedging says I'm choosing my forecast in such a way that no matter what the weather will be tomorrow, my track record can only improve. Now, the fact that it works, there is some work. Okay. Now, calibration cannot be guaranteed if, for example, Bary, the rainmaker, discovers my forecast before he decides on the rain. Because if my forecast is less than 50%, there's going to be torrential rain, just to make the point. And if my forecast is above 50%, like yesterday, 40 degrees of sun, 35, whatever, very hot, okay? We call this leaky forecast. So if my forecast leaks, not leaky like leaky roof when we get rain, but leaky like leaky weeks, when the information leaks out, okay? So leaky forecasts are when the forecast is known to the rainmaker ahead of the rainmaker's decision. So in that case, of course, I cannot guarantee calibration. As a consequence, if I'm using a deterministic procedure to decide on my forecast, which means that the history gives me exactly the forecast tomorrow, Bary can run the same algorithm that I'm using and know exactly what my forecast will be. So we are back in the leaky situation, and I cannot guarantee calibration. Okay. So now, let's go to continuous calibration. What's continuous calibration? Well, calibration says the following. For every forecast, I'm looking how well did I do. When I said 70%, what was the frequency of rain relative to 70%? When I said 75% or 71%, what was the frequency of rain relative in the days when I said 71%? It's a very discontinuous score because each forecast is treated separately. It's a different world. Now, we don't like discontinuous scores. So let's try to make it continuous. Let's try to smooth it out. I mean, there is a purpose for that, but that's the first thing. So that's what we call continuous calibration. So continuous calibration means, that's a continuous touch of the button, okay? Continuous calibration means that when I want to know how well the 70% forecast did, I'm not looking only at the days when I said 70%, when the forecast has said 70%, but I'm looking at all the days when it said more or less 70%. Okay, with some weights, with some smoothing factors, doesn't matter how you do it. Okay, any way you want to smooth it out. Okay, so that's continuous calibration. And here is a theorem. Here is another theorem. I can guarantee continuous calibration. Moreover, I can do it with a deterministic procedure. If you followed everything I said up to now, you'll say no way. If you don't say no way, it means you are not following. Okay? Okay, I mean, I just told you that, if I'm using a deterministic procedure, then the rainmaker is going to know what my forecast is. If he knows what my forecast is, he can screw me, yes? If my forecast is high, there will be no rain. If my forecast is low, there will be a lot of rain, okay? Nevertheless, since my score is a continuous function, I do it in a continuous way, I can guarantee continuous calibration. And this is not a proof. I mean, the proof, in a moment, you'll see it's not. I mean, I'll tell you something about the proof in a moment. The point is that suppose that I'm now playing something like 49%, 51%. That's what I'm playing on. So when I say 49%, he's going to make rain. When I say 51%, he's going to make shine, sun. Now, 49% is terrible. 51% is terrible. But around 50% is just right. Because half of them was rain, half of them was no rain. Now, that's not a proof that this works, but it at least shows you that there may be some hope. Okay? So that's a result which, of course, because deterministic means it works also when they are leaked. So there are various versions of that. So Foster, all of them include Dean Foster. I'm talking about, I think the neatest and cleanest version is the one in the 2021 paper, which really puts all this calibration thing, shows that forecast hedging is the common theme, that if you understand that, you understand everything, and everything is, all the proofs are the same for everything, just plug in the appropriate condition. Okay, now, to give you a hint why this works, another hint of why this works, which connects to the following, remember this plot, okay? That's how you do it to get calibration. To get continuous calibration means, first of all, you replace these dots with a nice continuous function. Well, I'm cheating a little, but roughly speaking, that's what you really are doing. And then, when you have a nice continuous function, then it is going to intersect the diagonal. That's going to be your forecast. Okay? However, okay, now, in order, for stochastic, yes.
Every day you update your data.
Every day I do that. Yeah, but updating is very easy because just one point moves. I made a forecast and only the history for that forecast moves, so there is the updating is easy. Okay, but wait a minute, because it's not easy. It's not easy. It's difficult, but in a moment I'm coming to that.
But with the validation of the forecast, I mean, the P's could be all separate. Is this your responsibility that they fall into a certain? Because you measure whenever you say P. If you never see the same P, how do you validate your
But continuous calibration always looks in a neighborhood. You look at an interval or some other smoothing out. Doesn't matter. Okay? And it doesn't matter how you do the smoothing out. You can do it any way you want. Okay? Okay. So the stochastic, so now this was rain, no rain. That's a one-dimensional setup. But you can talk about rain and snow and temperature and whatever. In principle, you can do the same exercise in a multidimensional setup. The beauty is that when I go to the stochastic forecast hedging was C1 and C2 with some probabilities, okay? That requires you every day to solve a minimax problem. Linear programming, that's easy. On the other hand, if you want to solve the continuous calibration, you have to solve a fixed point every day. Now, for one dimension, fixed point is easy. Continuous function intersects the diagonal, that's easy. But for 2 dimensions, fixed point and linear programming are very different creatures, yes? We have here computer scientists to attest to that. Yes?
So the minimax problem you're solving, is it though in like a grid over 3 dimensions, so not exponential, or not? Like, minimax are you going to solve? Like in how many points?
Yes, I mean, if you give me the error that you are taking epsilon, then you take an epsilon grid or something related to epsilon, and then the dimension times that. Yeah, so it's exponential in that. Yes, but still much easier than a fixed point problem, no matter what you do. Okay, okay. So this is an important distinction that, in fact, I think much of the literature missed. That there are things that you can do with minimax procedures. I'm ignoring now what dimension it is, and things you do with fixed point procedures, okay? And they are in very different classes of things, okay? So for stochastic calibration, minimax is enough. For continuous calibration, which is, as you saw, much stronger, you need fixed point. You need a fixed point every day, okay? Here is a slide that I was talking about. Okay, I don't know why it's here. Okay, now, why do we want continuous calibration? First of all, continuous calibration is weaker than calibration. If my 70% forecast is calibrated, and my 71% forecast is calibrated, and my 69 forecast is calibrated, their average, of course, is also going to be calibrated. But I can have the average being calibrated, as I said, 49% could be all wrong, 51% could be all wrong, but their average could be just right. Okay? So continuous calibration is a much weaker condition. So since I can guarantee the stronger condition, why do I go for the weaker condition? So for forecasting, makes no sense. Starting to use fixed points and so on to get a weaker result. Come on. Okay? It's good for something else. Okay? This is good for game dynamics. Okay? Now we are connecting to Nash. Namely, we can get Nash dynamics. Okay? So what are game dynamics? So roughly speaking, game dynamics, what are the game dynamics I'm talking about? So there are, of course, game dynamics of the sort. Exhaustive search, compute an equilibrium, just find exhaustive search or just follow a path, find an equilibrium, compute an equilibrium. That's not what I'm talking about. I want to talk about dynamics that are more natural. Dynamics that are more natural are of the following kind. A player thinks, okay, what's going to happen tomorrow? Oh, that's what I think is going to happen tomorrow. So I forecast the play tomorrow, and then what do? I best reply to it. Okay? I respond to it. Now, it better be that what I forecast is calibrated, otherwise the forecast makes no sense. Forecasts that are not calibrated are useless. Yes? If I think that Bernard tomorrow is going to play half-half and he always plays left, what's the forecast good for? But if I think that Bernard is going to play half-half, and indeed he plays half-half most of the time, that's useful. Okay? So we want calibrated forecast, and we want the response to be a best response. Okay? So let's look at this class of dynamics and ask what happens in the long run. So here is a famous result, calibrated learning, okay, Foster and Vora. That's the other paper of Foster and Vora, following the calibration paper, 96. That was a 97 paper, beautiful paper, that says the following. If every player makes a calibrated, there are epsilons everywhere. I'm ignoring the epsilons and the deltas, okay? If every player makes a calibrated forecast on what the other players are doing tomorrow, best replies to it, then in the long run, the time average of play is a correlated equilibrium. Beautiful result. Let me give you a proof. It's a triviality. The idea is great, but the proof is very easy. Because let's look at all the periods when the forecast was, my forecast of, let's say, now I'm going to use Bernard as my opponent. You are now free. You can drink your water. Okay? So I'm playing against Bernard. And let's look at all the days when my forecast was that Bernard is going to play 1/3, 2/3. Okay? What do? I best reply to it. Say top is my best reply to 1/3, 2/3. In the long run, if my forecast is calibrated, then Bernard is going to play about 1/3 of the time left and 2/3 of the time right. So when I get the signal, so my forecast is a signal. So I'm best replying to the signal. That's exactly correlated equilibrium. End of proof. People that never thought about correlated equilibrium, they have no idea, no clue what I'm talking about. I hope that people who thought about correlated equilibrium see that that's an immediate argument. Okay, that's very good. So I have to look at the time average of play. So I'm looking after 1,000 periods. I'm asking how often every n-tuple of strategies is being played. That's a correlated equilibrium, or almost up to epsilon. That's the result. Okay? Now, let's modify this and look at the continuously calibrated learning. What's continuously calibrated learning? Well, instead of calibrated forecast, there is going to be a continuously calibrated forecast, which is deterministic. And best reply I'm going to make it a continuous best reply. Also, that's technicality. Then we get the following result. Not the time average of play. Most of the periods, 1 minus epsilon of the periods, what people are playing is a Nash equilibrium, or an epsilon Nash equilibrium. So again, if I'm ignoring epsilon, okay, almost every period I see a Nash equilibrium being played in that period. I'm not talking about time average. Okay? Okay, let me prove you to it. Okay, forget that. So here is the result, as I said. Nash epsilon equilibria are played at least 1 minus epsilon of the time, which reminds me, how much time do I have?
9 minutes.
Oh, okay, good, perfect. Okay. Let me give you a proof. I like to give proofs. Okay. Now, the formal proof is, there are lots of details and it's not so easy, but the idea is quite simple. Okay. Let's look at the play at time t. What is the play at time t? The play at time t is you take the forecast at time t, which I call C sub t, and you apply, every player applies his own best reply to the forecast. Let's call this function g. So g is the function that maps forecast to what the players are playing, which is an n tuple of mixed strategies in principle. I don't know. It's an epsilon best reply. I don't know what it is. Okay? Now, suppose that this is calibrated. Okay? So here is what I claim. That, sorry. Okay? Here's what I claim. That continuous calibration implies that g of ct is approximately ct. Forget continuous. Let's talk about calibration. Every time the forecast was ct, the play was g of ct, was exactly the same. Every time the forecast was ct, because everybody applies a fixed best reply function to this forecast, the play is exactly the same play. By play, I mean the n tuple of mixed strategies that they play. So every time the forecast was ct, the play was g of ct. Now, if the forecast is calibrated, that means that the average action is exactly the forecast. So g of ct must equal to ct. That's what calibration means. Or approximately equals, because it's up to epsilon and because we have continuity and so on. So that's why continuous calibration implies that the play is approximately equal to the forecast. Okay? You have to change this. This is much too subtle. Okay? Okay. Now, I claim that this implies that the play at time t is an approximate Nash equilibrium. Formally, apply g to both sides. Okay? So g of the play is g of ct, okay? Which, because ct is like ct, is g of ct, which is the play. So the best reply to the play is the play. You recognize that's a Nash equilibrium condition. Okay? That's the proof. Okay? Now, why do we need continuous calibration for this? That's a good question.
Sorry,
because
can you explain where the epsilon fraction of rounds were lost?
No, I can, but offline, as you computer scientists talk. Okay? You see, I know the language. No, I don't want to get into that. I'm at a much higher level than the epsilons, I'm sorry. But I'll gladly explain to you. Everything is within epsilon. The best reply is within epsilon. The calibration is within epsilon. Everything. You have lots of epsilon around. In fact, the problem is to keep track of the epsilons and make sure that all the epsilons add up to just one big epsilon and not to, 1 minus epsilon. That's a problem. Okay. So why do we need continuous calibration? Why not use just regular calibration? Because continuous calibration is deterministic. The fact that it is deterministic means that I forgot to say it. I make all the players use the same forecasting algorithm. In fact, I can use the Central Bureau of Statistics to give everybody the forecast of what's going to happen tomorrow. Okay? The point is that because they are all using the same algorithm, and the algorithm is deterministic, they all the time say the same. If we were to use a stochastic standard calibration algorithm, it says that my forecast should be C1 or C2 is probability half-half. Even if we run the same algorithm, my algorithm says half-half. I toss the coin and I get C1. You toss the coin on the same algorithm and you get C2. We have different forecasts and the thing diverges. So the fact that our forecast is deterministic means that we are in tune all along and that we cannot get with stochastic forecasts. Okay?
Sergiu, sorry, just on this point then, does it matter that everyone is best responding to their forecast all at once? Sort of simultaneously, everyone is kind of...
Yes. So there is one forecast so think of a Central Bureau of Statistics that takes the history and says, my forecast of what's going to happen tomorrow, which is continuously calibrated, is that Bernard is going to play half-half, and you are going to play 1/3, 2/3, and so on. and I'm going to play 1-0. So what I do, I ignore what it says about me. Come on, they can't know what I'm going to do, and but I believe what they say about you, about the other guys, and I best reply to it. You ignore what they say about you, and you reply to that. And it's important that we all use the same forecast, otherwise it's not going to work. And the fact that it's deterministic allows it, which you cannot do it with stochastic. That's why we wanted that. And the fact that we weakened calibration to continuous calibration, that did not destroy things. In fact, in some places it improved it. Okay? So the important thing is that we have this very strange and unbelievable feature that despite the fact that the actions depend on the forecast, as I take the forecast, I best reply to it, free will, yes? You tell me what I'm going to do? No way, I know what I'm going to do. I'm going to best reply to that. Turns out that it was right. I did exactly what the forecast said, okay? So despite the fact that the actions depend on the forecast, I still get calibration. Not calibration, I get continuous calibration, but that's enough for dynamics, okay? It's subtle. This is subtle. This is a very subtle point and takes some time to understand. Okay, that continuous calibration allows leaky forecast, and nevertheless you don't lose calibration. Okay, fixed point I already talked about. Okay, let me skip that. Okay, but what I want to talk, and I hope that computer scientists will appreciate that a little more. We have two parallel universes. We have the minimax universe and we have the fixed point universe. Okay, they are parallel, not exactly. They meet on dimension 1, of course. But other than for any dimension bigger than 1, they are parallel. Okay? So the parallel goes like this. When we talk about forecast hedging, we do it stochastically using minimax. We do it deterministically using fixed point. Okay? What we call MM procedures and FP procedures. First one gives us a classic calibration. The fixed point gives us continuous calibration. In terms of dynamics, we get correlated equilibria as time average for the minimax world. We get Nash equilibria period by period, again, within epsilon in the fixed point world. Of course, now just if somebody comes and tells you, I can get fixed point, I can get Nash equilibrium with minimax, you know this can't be right. Okay? And there have been papers here and there, somebody claims, you know, I have a new proof of Nash, I have a new thing, using only minimax. No way, you cannot get fixed point without fixed point, okay? That's a fixed statement, okay? Okay, now, I want to show you, yeah, I'm almost done. I want to show you a slide from Nash's 80th birthday, not real birthday of the person, not not 75 of the paper, okay, at Princeton. And this was a slide that I put there. Here is a fact. And I said then, more than 50 years after Nash equilibrium, that was 2008, there are no general natural dynamics leading to Nash equilibrium. Okay? That's a fact. And I said, this is a fact, not like a computer science fact that means I'm lazy to prove it and it's probably false as stated, but some version of it might be right if I were to. Okay, no, this is the fact that nobody found such dynamics. Okay? That's what I said. And now, one has to understand what I mean by that. General, I mean in all, so that's it was a little longer than that. I give you the summary. General means in all games. Leading to Nash equilibrium means you converge to the set of Nash equilibrium, which means you get close to Nash and stay there. Not get close to Nash, then wander around and come back. That doesn't count as leading. That's a different story. By the way, okay, sorry, I'll talk about that. Now, what's natural? I don't know what natural is, but it should have some nice properties like being adaptive, being simple and efficient in terms of computation, in terms of time, being uncoupled, which I didn't mention here, but I don't have time for that, means you can only use your own payoff because you have no clue what the preference of other people are. And the claim is that this fact is in fact not just that game theorists are stupid and for 50 or 60 years couldn't find such things, is that there cannot be such things, okay? And I argue that through various work that Andreu and myself did and other people, Mansour and Babichenko, where is Yakov here, and so on. So how about continuously calibrated learning? How does this fit the picture? Well, it's adaptive, clearly. Whatever you think adaptive is, I mean, you're best replying, so it must be adaptive. It's uncoupled. you are best replying, so you only use your own payoff function. So far, so good. Well, it's not simple. Solving a fixed point problem every day, I don't know how many of you solved even once in your lifetime one fixed point problem. Not in R1, I mean, in R2. Okay? It's not leading to Nash equilibrium. It's not that you are getting close to some Nash equilibrium and stay there forever. It's that 1 minus epsilon of the time, you are close to some Nash equilibrium. Of course, there are other dynamics doing that. And you get period by period, which is very nice. Okay? And John Nash. This is a photograph of John Nash that I took while he was taking my photo of him taking my photo. Sorry, I got confused. What's written here is right, yes? John Nash taking my photo of him taking his photo and so on. So that's what we could call a Nash photo equilibrium. I think that's just right. That's from the 2010, the Brazilian Game Theory Conference. Thank you.
Okay, question. Okay, thank you. All right. Wow. So, simple question. You know, let me try to start.
Okay.
Let me try again. Hi.
I'll repeat it and then we'll, yeah.
Suppose that you're trying to calibrate against not some EV-level adversary like Bary, but against some stochastic process, you know, the given stationary law. Okay, so the weather is either good or bad every day with a certain probability. Okay. How long will it take you to be calibrated?
Well, okay, first of all, I think you heard this talk on calibrating. Well, didn't I give it in Toulouse, right? So the question of, so all this calibration analysis was worst case. I have no idea, nor make any assumption on Bary, on the rainmaker. It's completely arbitrary. I have no idea what he's doing. Could be an adversary, could be a stochastic process, something. How about the situation where I do know something? Can I do that? Can I get calibration and improve that? And that's a subject of calibrating, which I cannot talk about here, unless you'll give me another 40 minutes. But look on my webpage for calibrating. That doesn't reply to your question, however, how long it takes, because, but you can get bounds which come from the law of large numbers,
Yeah,
I think.
In this case, it's one of epsilon squared steps. You learn the Bernoulli like constant steps in the epsilon.
Look, I'm not a computer scientist, so I worry more about concepts than about exact things, but there are in the literature things like this. I'm sorry I cannot give you a precise answer, but maybe Kostis just gave you the answer. So.
Thank you. Thanks to both.
Okay.
Do you have the photo Nash took of you?
No, unfortunately not. Unfortunately not. I don't. Otherwise, I would put it here, of course. I mean, but Nash, if you remember Nash, he was going with his camera and taking photos all the time. I mean, that's so. I don't know where those photos are. It's a good question. Huh? Yeah. Hmm? No, but I know that he took my photo. That was clear. You heard the click, so that was. That's not fake. It's not AI made. Okay, if you are wondering. No, it's I suddenly remembered I found it in my old album from there. Okay.